Next chapter is not the correlation, it is about something like straight lines. So I thought I don't want to teach about straight lines to you because you have already done straight lines in A levels, right? So you are much better. So let's go to this section, that correlation. So in this section actually we talk about mainly the associations between two numerical variables. Say for example x and y. X can be for example height and y can be weight. Right? So one might ask, is there any association between height and weight? If there is an association, what kind of association is it? And so on. There are different questions that people can ask. Right? So, in order to answer that kind of questions, first of all, we have to collect data, right? So, in this case, we have to collect data paired, right? That means if you are collecting data, for example, height and weight, from each person, those two x and y both have to be observed, right? So, first person has a height, the same person has a weight. So, there is a pair of observations. Another person again gives you a pair of observations like that. It should be paired observations. So once you have paired observations, the best graph that you can look at to see whether there is any association, if there is any association, what kind of association is called the scatter diagram. Right? Scatter diagram. Scatter diagram is something like this. Right? Each point, xy point, is a point in the two-dimensional plane, so you can easily mark those points for different individuals. Right? So one axis will be x, the other axis will be y. So scatter diagram. Using a scatter diagram, you can answer this kind of question: is there evidence of a relationship? Right? What do you mean by relationship? Evidence of relationship. If there is some kind of pattern that you can see, then that is evidence of some relationship, right? Some kind of pattern. So you can easily see whether there is any pattern visible in the scatter diagram or whether there is no pattern. Right? If there is a relationship, if there is a pattern, is that pattern look like a linear pattern or a non-linear pattern? Linear pattern means here a straight line. So whether the points are close to a straight line, right, around a straight line, or whether they are close to some other curve type pattern, right? So if it is close to a straight line, we say there is a linear relationship. They don't have to be exactly on the line, on a line to say linear. If they are around some straight line, then we say there is some kind of linear relationship. Otherwise, we call it non-linear. Right? And then, linear or non-linear, is that relationship a strong relationship or a weak or moderate type of relationship? How strong, right? Strength. What is the strength of the relationship? Right? Are there outliers? If there are outliers, whether the outliers affect the relationship, those kind of questions. Right? So the best graph to look at is actually the scatter diagram. Right? So here I have shown you some examples of scatter diagrams. So this kind of one, right? So you can see that these are around some straight line. If you draw a straight line through the points, some of the points will be above, some of the points will be below. Or there is without any particular pattern in that one, right? So that therefore is an example of a linear relationship, what we call straight line relationship. There is also a linear relationship. You can draw a straight line through the points. So in this one, they all have some relationship. There is no relationship here. Right? This picture shows there is no relationship. But all the others, there is some kind of relationship. These two can be considered as linear relationships. these are all some kind of non-linear relationships. And then if you consider the linear relationships, right, all these are kind of linear relationships. Right? Using the graph, we can also see how strong the relationship is when it is linear. Similarly, when it is non-linear also, if it is going around some curve, whether the points are close to the curve or whether they are somewhat far apart from the curve. Right? So this is an extreme case where all the points are on the line itself. So that is called a perfect linear relationship between x and y. Perfect. Right? In this case, actually the line has a positive slope, therefore we say there's a positive perfect linear relationship. Positive, perfect. Like if we had a set of points on a line with a negative slope, then we say negative perfect linear relationship. So not only the strength, we can talk about the direction, positive direction or negative direction. If the slope is positive, we say a positive linear relationship. If the slope is negative, we say negative linear relationship. So in this one, you have a negative linear relationship. All these are positive linear relationships. Right? So this is perfect. If you consider these two, you can see that, of course, depending on the scale, these pictures will be different. So let us assume that the scale is the same here. Right? If you have the same scale, what can you say about this and this? They both are positive, show positive association, but these points are more close to the line than this one. So therefore we say here somewhat stronger relationship, here somewhat weaker relationship. Right? And similarly here somewhat maybe moderate relationship, negative. Right? So we can answer that kind of questions roughly using a scatter diagram. Now, these are some outliers, for example. These are actually, in the previous situation, we were talking about univariate outliers for one variable. Similarly, we can talk about bivariate outliers. Right? So here, all these are points bivariate. Right? Each represent two variables. So the bulk of the data is this one, this area here. So when you consider two-dimensional, you can call it two-dimensional outliers, for example, some outliers can be outlying with respect to their x value. Some are outlying with respect to y value. Some are outlying with respect to both. For example, here this picture, the bulk of the data are between these two x values. Bulk of the y values are between these two y values. Right? So if you consider this observation, the x value is in the normal range, but the y value is quite different from the bulk of the y value. So therefore this observation is, we can say it's outlying with respect to y value, outlying with respect to y value. If you consider this one, that's outlying, maybe it's in the same level as some of these observations, so therefore y value is not that much outlying, but the x value is outlying here. So that can be considered as an outlier with respect to x. This value is outlying with respect to both x and y, right? Quite different from the x values and somewhat different from the y values as well, both x and y values. So there, you can see if there are outlying values also, you can see from the scatter diagram. So therefore scatter diagram is a very useful graph when you have bivariate or two-dimensional data. Right. So here there's an example from the book, Carl Pearson's study on heights and fathers and sons. So I'm not sure whether they talk about only father is only one person, but sons, there may be several sons. So I don't know which son they considered. Whether they considered fathers with only one son, or maybe, I don't know. It's not clear in the data. So anyway, they have looked at some relationship between father's and father's height and son's height. The prop is not here, so what they are talking about? So that is an example only. I don't have the data. Right. So that is one example. Now, when you consider this kind of relationship, there are two words coming usually. One word is the independent variable, the other one is the dependent variable. Independent variable and dependent variable. Sometimes they have some other names also. Independent and dependent. Dependent variable is also called response variable. Independent variable is called explanatory variable. These two words are more meaningful than these ones, but these ones were the earlier usage. Right? So when you have two variables, if you are only looking at the association, that is the only purpose, you can take any variable as independent variable and the other variable as the dependent variable. It doesn't matter. But if you are only interested in the association. But most of the situations where you are interested in association, you are also interested in some kind of prediction. Right? You want to be able to predict one variable when you know the value of the other variable. For example, if you are finding the relationship between height and weight of adult males, for example, you first of all you want to see what kind of relationship, whether you can get some mathematical equation for the relationship between height and weight and so on. So that is another thing called regression analysis and so on. Once you know the height of some person, you may want to predict without weighing actually, you may want to predict. Right? Or maybe given the height, you want to see whether that person is in the range of the necessary height, or whether he is too short for that height and so on, too light for that, or too much weight for that height and so on. Right? So we want to be able to predict. If you want to predict also in that situation, these two words are important. Right? So when you're in a situation where you want to predict one variable using the other one, the variable that you want to predict is called the dependent variable. So if you want to predict the weight using height, weight will be the dependent variable. Dependent. The other variable is called the independent variable, therefore. So we think that the weight is depending on the height. Right? So once you know the height, then you should be able to predict the weight. So in that case, weight. So that is denoted by usually y, and the other one is denoted by x. And the response, on the other hand, is the one that you want to predict. Right? Response. Explanatory means the response is explained by the other variable, explanatory variable. So we think the relationship, there is a relationship, y is the response, and it's explained by x. So in that case, x is the explanatory variable. So this is useful especially when you want to do some kind of prediction. If you want to get some equation related to x and y, right? So in a situation where you have, say, height and weight, father's height and son's height. Suppose you have two variables, and now you don't know which one should be taken as x, and which one should be y. In this case, what do you think? You have father's height and son's height. As I mentioned, if you want to only look at the association, doesn't matter, right? So, whatever, if you want to predict, what will be the more meaningful thing to predict in this case? Sun side, right? Because father comes first, right? Son's height may depend on father's height, but the father's height is not going to depend on son's height. So generally, that's the way, right? The one that comes first is the independent variable, the other one is the dependent variable. Therefore, but there's no rule saying the other way cannot go. You should not look at the other way. If there is some particular reason, for some reason that you want to predict the father's height when you know the son's height, you can do that also. In that case, of course, you can take father's height as the dependent variable and son's height as the independent variable. So it depends on what you really want to do, right? In most of the cases, there is a natural choice also. But in a particular problem, that choice may be the other way around because of some particular reason, right? So therefore, real way to look at it is what you really want to predict is y, the other variable is x. So this is the scatter diagram between, I think, father's and son's height and father's height. So what can you see? If you get this scatter diagram, how would you explain? Is there a relationship? Is there a visible relationship? If there is a relationship, what kind of relationship? How strong do you think it is? And so on. How do you explain? Huh? Yeah. So mainly, this first of all, it looks like some kind of linear relationship, right? Because it's reasonable to think that it's going up, right, around the straight line. So there seems to be, so therefore we can say positive, direction is positive. Type is linear, right? And you can add another adjective depending on your view, for example, whether it's a strong or moderate or weak, right? That's going to be a little bit subjective, that whether you are going to decide whether it's strong or weak or not. It's going to be subjective. It's also depend on the scale, right? If you draw the same thing in a large scale, these points will be farther away from the straight line. So that one might say the same thing, weak in that case. Right? So it depends on the scale. So we should have some way to everybody to get the same answer. See, let's see how to do that kind of answer. For example, if I ask from these four people might say 2 or 3 different answers depending on how they view it. Right? But there's another way that you can draw the same graph where everybody will give roughly the same answer. So that is an important thing. Right? And also, another thing is that we can get a numerical measure if you have a linear relationship. Right? If you think that there is a linear relationship, even though you cannot probably say whether it's a strong or weak or moderate relationship, you can get one number. Everybody will get the same number in that case, a measure of the strength. Right? So once you get the number, because everybody get the same number, then everybody will be interpreting the same way. So that is a good thing. So that number is called the correlation coefficient. Correlation. The correlation coefficient is suitable only if there is a linear relationship. Right? So first of all, before some people, again, I have seen that people calculate correlation coefficient even without looking the graph. Right? In a lot of research papers, they just calculate correlation coefficient and interpret it by looking at the number. They have not even looked at the scatter diagram. So that can be, therefore their interpretation can be completely wrong. Right? Because correlation coefficient, first of all, meaningful only if there is a linear relationship. So in order to see whether there is a linear relationship, first we should look at the graph. Otherwise, without looking at the graph, we cannot see whether there is a linear relationship or not. Right? If there is only a linear relationship, we can calculate the correlation coefficient, and by looking at that thing, of course, we can interpret whether it's a strong one or moderate one or weak one or something like that. So therefore, when you have two-dimensional data like this, if you want to study about the relationship, I think very important to look at the scatter diagram first. So here what we can see that this kind of shape is called football shape. In the middle, so you can actually calculate the mean of x values. You have several x values and several y values. For each x you have a y, but you can calculate the mean of x values as well as standard deviation of x values separately, and mean of y values and standard deviation of y values. So the mean of x values will be somewhere here in the middle. Mean of y values will be somewhere here. So therefore the mean x bar y bar value will be somewhere in the middle there. It doesn't have to be on this line. They have drawn line here. We'll talk about that later. This is called the SD line. But yeah, actually the average point will be on the SD line. Right? So the average point will be somewhere there. And then around that there are a lot of observations. But when you go farther away, right, the number of observations become less. So therefore, generally, this kind of shape is called a football shape. Right? Not our football actually.
American football. American football.
American football. Right? We call it rugby, right? So they call it football shape. And we can look at something, if you want, you can look at some kind of conditional distributions also. For example, what is the distribution of, how the distribution of son's height when the father's height is approximately 72, right? So for a given value of one variable, what is the distribution of the other variable? So if you consider all the sons whose fathers are around 72, so their heights are in this range. Sons' heights are in this range. Right? But if you consider some other range for the fathers, for example, this one, their heights are in some other range. Right? So you can see that the shape and therefore the range and the distribution of the son's height depends on actually the father's height. Right? So you can look at all those different things using a scatter diagram. So generally, if I ask you to, if we want to describe this kind of graph using some numbers, then what can we use, right? Like when you have a single variable, right? If you have only just a set of numbers from one variable, we learned that one thing we can draw is we can draw a histogram, that is a picture we can draw, right? We can describe that kind of picture using some summary measures like mean, median, depending on the shape and so on. If the shape is skewed, we might look at the median instead of the mean, and interquartile range instead of the standard deviation, right? And those two will not be enough sometimes. If it is skewed, we might need the percentiles as well, and so on. Right? So those are numbers. So similarly, in order to explain this kind of graphs with some few numbers, what are the numbers that you can use? As I mentioned, you can mention about the mean of x values. So therefore, we can get some idea about the middle of x values. And similarly, we can express middle of y values, mean of y values, for example. And we can also give the SD of standard deviation of x values and standard deviation of y values. So if you know the mean and if you know the standard deviation, we can get some idea about roughly the spread about the x values and similarly spread of y values, and thereby we will be able to draw the football then, right? So we know that, okay, x values are between these two and y values are between these two. So therefore, roughly it should be like that. So get an idea once you say it's football shape. Right? But is there enough? With the same range, right? You can have a football like this, or you can have a football like this. Right? It's possible. Right? So if you say the mean and the standard deviation, it doesn't give you the complete picture. Right? Because then it doesn't explain the spread. It doesn't explain the spread. So we need some other measure also which talks about the spread. So if you have all those, then we can have a complete picture roughly about the football that we have. So that is where the correlation coefficient is important. The correlation coefficient gives you an idea about the spread of the football around the center line. Not the center line actually, this line is called the SD line, I will come to that later. So therefore, you can have rough idea about the football if you know the mean of x value and standard deviation. Roughly you know if roughly x values are normally distributed, we know 95% of the values are going to be within 2 standard deviation from the mean, right? So if the mean is here, so this value will be x bar minus 2 times standard deviation, this will be x bar plus 2 standard deviation. So that gives you roughly the 95% range of the x values. And similarly you can find out roughly the 95% range for the y values. So by doing that you can roughly get some idea about the football. But still it doesn't give you about the spread of the football itself, because you can have a football like this or like that within the same range. Right. So I have explained that same thing here. So these are two different relationships, but x mean values are the same. X and y have the same mean, here 50-50, and this one has mean roughly this value is same as this one. Standard deviations are roughly the same, but two pictures are different. So therefore we need some measure to explain the difference between these two shapes. So that is where we use the correlation coefficient. Correlation coefficient. The person who suggested that was Pearson, so therefore sometimes we call it Pearson's correlation coefficient. So remember, therefore, Pearson's correlation coefficient is a measure of the strength of a linear relationship. So you can use, it is meaningful only if there is a linear relationship. When you have a non-linear relationship, there is no point even calculating correlation coefficient. That many people do, right? But that is completely meaningless. Right. So this is the way that you calculate the correlation coefficient for a sample of data. It is the average of the pairwise products of the standardized values. Right. So you have x values and y values, right? x1, y1, x2, y2, and up to xn, yn. So you take these values and each value you standardize. Right. So from each you get, for example, z x1, z x2, and so on, z xn. Right? Subtract the mean of these values from each value and then divide by the standard deviation. So that's that part. And similarly standardize these values. So let me denote them by z y1, z y2 up to z yn. So from each of these values subtract the mean of those and then divide by the standard deviation of those. And then take the product, this times this, plus this times this, plus this times this, and so on. Take the product. So that's what the R is. Correlation coefficient, sample correlation coefficient is denoted. And product, and then take the average actually. Right? So take the sum of those products and then divide by n. So that is what the correlation coefficient is. It is denoted by simple R usually. So for example, if you look at a simple example, suppose you have these xy pairs. So what you have to do is, first of all, calculate the standard units, standardize x values. So take away the mean from each x value, so in that case you will get these values, and standardize y values, then you get, and then take the products, and then take the mean of these values. So in this case, when you calculate it is 0.4. So that gives you the strength of the linear relationship. Now in this case we didn't look at the graph, so this will be meaningful only if it is a linear relationship, so let us assume that it is. So in that case, this value gives you some idea about the strength. So in order to interpret that, we need to know certain other things about R also. Here I have given you another formula that sometimes in a lot of statistics books they are using this formula, but I think the previous one is more meaningful than this one. This is a little hideous also to look at. So these are the things that we have to know about this R. Whenever you calculate R, right, of course you can calculate R even if the relationship is not linear. Right? Mathematically you can just calculate, no, you can take the standard deviation and mean, standardize. There is no rule saying you cannot do it, but that is not meaningful, that is the thing. Right? Doing it is not useful. But whenever you calculate R, even if it is a linear relationship or not, this value is always between -1 and +1. Right. Remember, it is meaningful only if it is linear. So it's always between -1 and +1, inclusive this. Right? R can be -1 or R can be +1 also. But those are the extreme cases. But in general, otherwise, it's between those two. And the other thing is, R is a unit-free measure. Right? Because when you take the standard units, as I mentioned earlier, this quantity is unitless, this quantity is unitless, therefore the product is unitless, and therefore R will be unitless. Whatever, for example, X can be in grams, kilograms, or Y can be in meters or centimeters, still R doesn't have any unit. Right? So that's a good thing also, because you can use it even, we will see later on, actually doesn't matter what scale, what unit you use, your R will be the same thing. Right. So your R will be exactly -1 if your points are on a straight line with negative slope. Right. If all the points are on a straight line, it can be like this, or it can be like this, or it can be like this. In all these cases, if the points are on a straight line, R will be -1. Right? So those are actually not practically important situations. So when there is almost no situation where R is exactly -1. And similarly, if the points are on a straight line with positive slope like this, or like this, or like this, R will be +1. Right? So those are the two extreme cases. Otherwise, now we should be able to interpret these values in some way. Actually, interpretation, again, in different books they are talking about different interpretations. But one interpretation that I have seen is that they have divided this scale between -1 and +1 into several parts, like 0.25, 0.5, 0.75, and then +1 here, and then -0.25, 0.5 negative 0.75. Right. So in one book I have seen, I think this is somewhere fair way to explain it. If your R value is between these two numbers, including 0 but close to 0, then usually you say there is almost no linear relationship. Right. Theoretically, if R is exactly 0, that means there is no linear relationship. But practically, when you calculate these things, if you get a number between -0.25 and +0.25, usually we interpret as there is no linear relationship. So if R is between these two numbers, then we say there is a positive weak linear relationship. And similarly, if R is here, we say negative weak linear relationship. And if R is here, then we usually say moderate positive linear relationship. And similarly here, moderate negative linear relationship. If R is somewhere here, then we say strong, right? Strong positive, strong negative linear relationship. So if you use that interpretation, point 4 will be somewhere here. So it indicates, according to that interpretation, we can say there is a weak positive linear relationship between the two variables x and y. Right? But that is not a universally accepted one, right? Because it depends on the discipline also. In sciences, usually this is the definition, this is the interpretation. But in sometimes social sciences, it's very difficult to get large R values, especially when the data are coming from observational studies. Very rarely only people have R values like 0.7, 0.8 and so on. So in that case, sometimes even with 0.5, they say that's a strong relationship. So depending on the discipline also, the interpretation is somewhat different, right? So if you look at in different research papers, therefore they have interpreted it in different ways, especially depending on the discipline. Right, so these are some examples. Depending on R, we can say this is a negative perfect linear relationship. So according to our one, this is going to be moderate, I think, negative moderate linear relationship.
Is it negative 0.6?
0.6, yeah. Because it can be 6. It's between.
Can't see the point.
Yeah, 0.6. So R theoretically it is not exactly 0 here. This will be somewhere close to 0, right? But this one is positive exactly 1, so that's a positive exact perfect linear relationship. This is 0.3, so that's a kind of weak positive linear relationship. This is R is exactly equal to 0. Again, R is equal to 0, not exactly 0, again approximately 0. R is negative 0.3, R is 0.5 here, R is negative 0.7, this R is 0.9, the other one is 0.99. So we can see that it gives you a fairly good interpretation, right? Of course, these numbers capture to a certain extent the strength, right? We can agree that, for example, this one is more stronger than this one, right? So that is reflected by the number here, right? Negative, of course, but it is 0.99. This is positive, but 0.9. So the number actually is kind of proportional to the strength. Okay, so that is about the correlation coefficient. So one important thing is actually draw the scatter diagram always if you are considering the relationship between two numerical variables, and use the correlation coefficient as the measure of strength only if you think there is a linear relationship. Otherwise, don't even calculate it. It's not going to be meaningful. Right? So there are other measures called strength of nonlinear relationships, but they are not in your syllabus, therefore we are not going to talk about those. Right. And then in the book, there's something called SD line, standard deviation line. So SD line is actually kind of a theoretical line. Now suppose you have two variables and suppose you have calculated x bar, the mean of x value, and y bar also you know. So therefore you can find out x bar, y bar point. And suppose you know the standard deviation of x and some standard deviation of y also. So let's look at x bar plus standard deviation of x. So that is, if you consider this to be a standard deviation of x, so this value here will be that. And then similarly calculate y bar plus standard deviation of y. Suppose this is the standard deviation of y value. Right? So then the line that goes through this and this is called the SD line. Of course, that is if you have a positive linear relationship. Right? If you have a positive linear relationship, your SD line will be defined like this, right? Connecting the center point here, x bar, y bar, and then x bar plus sx and y bar plus sy point. That is called the SD line. And that line is actually the line on which all the points will lie if r was equal to 1. If r was equal to 1, all the points will be on this line. And similarly, if you have a negative relationship, it's going to be the other way around. So that is again like this. So that is what the SD line is. In this case, the slope is positive, that is equal to SD of y divided by SD of x. On the other hand, here, if you have a negative relationship, in that case, it will be negative of this thing divided by that. That is what the SD line is. Theoretically, it is the line on which all the points will lie if the relationship was exact. Right. Okay, so now let's try to understand how the correlation coefficient, or why the correlation coefficient gives a measure of the strength of the linear relationship, right? So that means by looking at the R, how do we kind of view or perceive the size of the strength of the linear relationship? One thing is, by the sign of R, we can decide whether it's a positive linear relationship or negative linear relationship. So sign should show whether it's positive or negative. And also the size of the R should tell you how strong the relationship is. Right? So let's see how, for example, when you have a positive linear relationship, why R becomes positive. When you calculate R, why does it become positive? When you have a negative linear relationship, whereby you get a negative value for R. Remember, R is equal to the mean of Z x I from 1 to n times Z y I. So this is equal to 1 over n summation I from 1 to n xi minus x bar divided by sx times yi minus y bar divided by x bar. So if we have a positive relationship like this, what you can see is that most of the, now this is the x bar value, this is the y bar value, so this is the center point. So if you have a positive linear relationship for these values, what will be the sign of xi minus x bar divided by sec x? For these values, that part will be positive, but this part will be negative because it is below y values, right? So this part, this quantity will be positive here because that is xi is greater than x bar, so that will be positive. This is always positive. For this, yi value is less than y bar, therefore yi minus y bar will be negative. So this product coming from these observations will be negative. And for these points, all the points, this quantity will be positive, this quantity will be also positive. Therefore, the product will be positive. For this, both quantities will be separately negative, but the product will be positive. But here, positive and negative, product will be negative. So if you have this kind of relationship, now you will be looking at the average of these products now. So there will be some products which are positive, some products which are negative. But most of the products like this will be positive. Only few products will be negative. So when you take the average, therefore, generally the average of the products will be positive. So that's how you get a positive value for R if you have a positive linear relationship. And similarly the other way around, if you have a negative linear relationship, you can explain it in the same way. So I have mathematically written down here, you can understand that. And then we should also see that if there is a strong linear relationship, we should get R value somewhere close to positive 1 or close to negative 1 depending on the direction. And similarly, if there is a weak relationship, we should get a value close to 0. Right? So how do we get that kind of values from this one is also explained here. I'm not going to explain that by taking time, but I have written down here. I think you can go through it because you know the mathematics. Next time if you have any questions, we will discuss it. Please go through. I have explained if there is a strong linear relationship, how R becomes close to 1. I have explained it. Right? So the general idea is if there is a strong linear relationship, we should be able to write down yi values approximately equal to a plus bxi for some a and b, right? Because if there is a positive strong linear relationship, the points xy points must be close to a straight line. So therefore we should be able to write down yi is approximately equal to this. So using this idea, you can show that if you calculate, assuming that yi is approximately equal to this thing, you can show that r will be close to 1 in that case. Right? So that is the idea that you have to show. I have done that. So please go through that. You can, I think, you should be able to understand that. And similarly, if there is a weak relationship, then there is no relationship like that, and therefore r will be 0. So that I have explained that also. So like that we can explain why R is a suitable measure to measure the strength of the linear relationship. So it definitely gives you the direction as well as the strength. So go through that. Okay, that's the end. Right. So of this section, but there is another part called the other chapter. Next chapter is also continuing with the correlation. So let me go to that. Next chapter. Half an hour. So in this section we discussed the importance of the scatter diagram, right? And then using the scatter diagram, what are the things that we can get? For example, see whether there is an association or not. If there is an association, what kind of association? Linear or non-linear, right? If, for example, linear, then we can talk about the correlation coefficient. So, whether there is a strong linear relationship or a weak relationship, also by calculating R, we can get some idea, right? So, the next chapter is also correlation continued. So about correlation. So there are other things that we have to know about correlation. Correlation, as I mentioned earlier, correlation doesn't depend on the units that you are using. That is one thing. Now suppose, for example, you have two variables x and y. So we have paired observations x1, y1, x2, y2, and so on up to say xn, yn. Suppose you calculate the correlation coefficient and you get the value R, some value R. Right? Now suppose somebody else for some reason have got instead of y values, he has got say w values, wi equal to y1 plus some constant, y2 plus c, y3 plus c, and up to yn plus c. So that is a new set of values. We have added same constant to y. Right? If you calculate the correlation between x and w, it will be the same as the correlation between x and y. Right? So R between x and y is the same as R between x and w when w is equal to y plus a constant. Now, if you say you have another variable, say v is equal to constant times y, some constant times y. Right? If you calculate r x times v, it will also be the same as r, still the same as this thing. Right? So, in general, you can, if you apply a linear transformation, right? right? Not only adding a constant but also multiplying and adding. Still the correlation will be the same. Strength of the correlation will be the same, right? You can mathematically prove it. Right. So here I have shown this using some simple example. Actually, this fact is a different one. Now, as I mentioned earlier, if you are considering only the association, you can take x and y as independent or dependent, whatever the way you like. Right. So that means doesn't matter whether x is that or y is the other one, or the y is the x and the other way. Right. So the correlation between R between x and y is the same as R between y and x. Right? Why is that? How is that? Because very simple, R between x and y is equal to average of z xi times z yi, right? R, right? This is the same as 1 over n z yi times z xi, right? You can interchange the product. So by definition, this is equal to R between y and x. Right? So therefore, that is very clear. Right? And in the same way, you can prove these ones also. Right? Once you can transform maybe one variable or both variables using a linear transformation. If you transform that and consider the correlation between the new variables, still the correlation will be the same. So generally, therefore, if you apply a linear transformation to x and linear transformation to y, and if you consider the correlation between the two new variables, still the correlation will be the same as the correlation between x and y. So I invite you to show that one using this result here. For that, something important I will tell you. For example, suppose w is equal to ax plus y. Now, if the mean of x values is equal to x bar, standard deviation of x values is equal to say sx, what will be the mean of w values and standard deviation of w values? So these are ax plus bc. Yeah. What will be the mean of w?
W bar equals ax bar plus b.
Yeah, w bar will be equal to ax bar plus b. What will be the standard deviation of w values?
A times x is s6.
A times 6, yeah. B doesn't play any role there, A times 6. How do you explain practically this result? Why does it become like that? Mathematically, of course, we can prove by definition, but practically, how do you explain that? Why B is coming here and B is not coming here?
So when you add the b value, the graph goes up and down, but the range doesn't change. So the same thing when the b is 0.
Yeah, when you multiply, of course, the number
Yeah.
becomes larger according to proportionality. But when you add a number, everything, so that new one becomes just shifting to this side without changing the dispersion doesn't change. Right? If you have, say, for example, ax values will have a different dispersion than x values. But whatever that distribution, when you add a b value, the whole distribution will be shifted the same way without changing the the dispersion. Therefore, b doesn't play in the dispersion. So that's why. Right. So these results will be useful to you when you find out, say, suppose w is equal to ax plus b and b is equal to, say, some other, say, c y plus d. Right. So suppose the correlation between x and y is rxy. I am asking you to find out wv or vw, whatever. Find out this one. In that case, you will need these results, and you will be able to show that they are the same as rxy. So that's what I am asking you to prove. Right? using the definition, please do that. Right. So this is an example where even though you don't interchange the two variables x and y, so here what we have is some temperatures. For each day we have a minimum temperature and a maximum temperature. So each day we have two values. So if you take minimum as x and maximum as y and calculate r, then you have this number. If you take maximum as x and minimum as y, still r is the same, so it should be very clearly, right? And adding a number and multiplying the numbers doesn't change also. For example, if you consider this transformation here, suppose somebody has measured the temperature in one town, two towns actually, temperature in two towns on different days. Right? So today I measure the temperature in New York and Boston in Fahrenheit. Somebody else measure the same thing in Celsius. Right? So if you plot the histogram, the scatter diagram for the Fahrenheit, you have this one. For the Celsius, this one. Right? So by looking at the graph, we cannot say whether the correlation is the same or not. Different people might have different answers. And somebody might say, in this case, correlation is higher than this one, right? But that is because of the scale, right? If you really calculate the correlation, in this case, correlation is the same, R is the same. Right? Now, what is the relationship? Actually, C is a linear transformation of F. C is a linear transformation of the Fahrenheit. So therefore, doesn't matter when you have a linear transformation, the correlation is preserved. Right? So that's what it shows you. Okay. Now another question. So this is again about the scales and graphical interpretation, visual interpretation, right? As I mentioned in the beginning, so by looking at the graph, we can say that whether there is a positive linear relationship or not, whether it is linear or not. That is possible to say, but it's not very easy to talk about the strength of the relationship, because the strength depends on the scale you choose, right? So I mean, actual strength doesn't depend on the scale, but the visual strength depends on the scale, right? So here, for example, I have two scatter diagrams. In this case, what is happening is actually they both have the same mean in x and y, the same mean. The scales are the same here. Right? This is going from 0 to something like 25. This is going from 0 to 15. Scales are also the same. Right? Now, if you look at these two graphs, which one do you have? Do you think what do you think about R? Correlation. Not the value of R I am talking about. As you visually look at it, which one do you think they have the same strength of the correlation, or one is more stronger than the other one?
First one is strong.
Yeah, it looks like this one is stronger, right, than this one. But actually, the correlation coefficient is the same in this case, these two. The reason here is, even though we have the same scale, for these data, Sx is this value 3 and Sy is 1. For these data, Sx is almost the same as this one, but Sy is different. This is twice of that. Okay? So you can see that X range is roughly the same here, but the Y range here is larger for this one. Right. So actually, just by looking at the picture, it is not easy to say therefore whether they have the same strength or not. Right? Because the standard deviations are different. So when you calculate the standard units, remember R is equal to product of the average of the products. So when you calculate the standard units, you divide by Sx and Sy, right? So therefore, standard units depend on Sx and Xy. Right? So therefore, if you want to really compare two graphs, only two graphs, and by looking at the graphs, if you want to say compare the strength of the correlation, the original data, original scatter plots are not going to help you sometimes, because the two data sets may have different standard deviations, and therefore you may have the same wrong impression like here, right? So in order to avoid that, what you can do is, if you convert x values into standard units and y values into standard units, and then plot like this, then both graphs will look like the same if r is the same, right? So if I standardize x values, these x values here and y values, and plot the scatter diagram for these data, x and y values, standardized values, and similarly for these standardized x values and y values, and plot these, both graphs will look like this now. So this graph came from the previous this graph. So this axis now, in the second one is standardized units. Standardized units. Earlier you had numbers up to 25 or so, but now it's between -4 and +4 here. Similarly -4 and +4 here. So now you can see, I mean, everybody will agree that they have the same strength. So therefore, if you want to only visually compare two graphs and say about the strength of the relationship, it's best to look at the standardized, the graph coming from the standardized units rather than graph coming from the original data. So that's something that you should remember. Right. Okay, so at the last point, we will talk about some precautions that we have to take when we interpret R. Right. One thing you already know, that you should interpret R only if there is a linear relationship. But there are other things that you have to be careful also. So these are also, these things also can be checked with the scatter diagram. One thing is that this R value will give you the idea about the strength of linear relationship only if the scatter diagram is roughly football shape. Right? If it is not roughly football shape, then R value will not be very useful. So that is, remember, only if you have this kind of things, most of the things will be positive here, and therefore negative, and the average will be positive with the positive value. But if it is not football shape, that will not happen. So therefore, one thing is, look at whether it's kind of roughly football shape scatter diagram you have. So therefore, always plot the data, draw a scatter diagram before you do anything, and then check for outliers. If there are outliers, of course, R can distort, the value of R can be distorted very much. So for example, I will show you a few examples. So if you have this kind of graph, and without looking at the scatter diagram, if you calculate R, your R will be something like 0.38. If you look without looking at the graph, if you calculate R, you will get this. So you will interpret, then you will say there is a weak linear relationship, positive linear relationship. But actually, this is a kind of outlier. So if you, for some reason, if this was a mistake, you can easily remove it or correct it, right? So once you do that, you will have this one, right? So this is a very strong linear relationship, right? So that error can happen if you just calculate R without looking at this thing and identifying R and doing something meaningful with it, right? So therefore, it's very important to look at the graph and deal with the outliers appropriately. Of course, in this situation, most probably there is an error, recording error or something, right? Very rarely only this kind of observation comes in a two-dimensional data set, right? But that's very rarely possible. In that case, of course, R is not a suitable method. R is not a suitable measure in that case, because it's not a football shape or any kind of shape. Right? So similarly here, you have some kind of linear relationship, but because of this is an outlier. Again, R becomes very small, but if you remove that, Of course, you remove it only if it is a real blunder outlier, wrong outlier. If that is the case, then R will be something like 0.828. Right. So therefore, you have to be careful about outliers in order to see whether there are outliers and identify and do whatever the meaningful thing to do. You need to look at the scatter diagram. And of course, as I have already several times mentioned, R is not meaningful if the relationship is non-linear. Right? So suppose you, without looking at these graphs, you calculate R for this kind of situation. Right? Your R will be close to 0. Right? So people do that kind of thing without looking at, calculate R, so R is close to 0, and then they interpret it as there is no relationship. That interpretation is wrong. Why is wrong? There is a relationship here. There is a pattern. But there is no linear relationship. There is no linear relationship. Right? So actually, if you wouldn't even calculate R if you look at this thing. Right? There is no point of getting R equal to 0 by looking at this thing and then say there is no linear relationship. It's already clear that there is no linear relationship. So that kind of things are important. And this one, if you calculate again without looking at the graph, R will be 0.94. So one would say there is a very strong linear relationship. But this is not a linear relationship. So if you say there is a very strong linear relationship, that is again a wrong interpretation. And few more things, confounding by other factors. Like if you have this kind of graph, it's possible to have this kind of graph. For example, suppose there are two groups. You are looking at variable x and y, but this is the scatter plot for one group, this is the scatter plot for the other group. Right? So if you consider altogether this as one picture and calculate the correlation coefficient, it will be a high value because of this, it will give you a high value. Then if you interpret that value as a strong positive linear relationship, that is actually a wrong interpretation. Why? Because here actually you have to interpret, if you have this kind of picture, you have to interpret this group wise. Right? Group is a other factor on which the relationship depends. Right? The relationship between x and y depends on the group. For example, this may be a male group and female group, whatever. Right? So within each group there is no relationship, linear relationship. There is no linear relationship. So you have to calculate R if you want. Right? There is no point of calculating R in this case. You can even by the graph you can say there is no linear relationship. Right? But if you put all this together, then this is completely wrong. So that is again tells you looking at the graph is very important. And sometimes, especially these ecological studies, people calculate correlations between averages rather than correlation between individual observations. So for example here, people have calculated the correlation coefficient between a rate of cigarette smoking and rate of lung cancer for different countries. So take one country, find out what percentage of people are smoking and what percentage of people have lung cancer. So two numbers for one country and another two numbers for another country, another two numbers for another country. Right? So if you plot these things and calculate correlation coefficient, they have done it and they have seen that it is very high, 0.7. But when you have this kind of situation, these averages, correlation between averages is not a good thing to interpret. Because countries don't smoke and countries don't get lung cancer, it's people, right? So only people, you have to get the data from individuals, otherwise you cannot come to that kind of conclusion by looking at the correlation between averages or ratios from different groups. Right? So that is something that you have to remember also, because for example in a country, right, so in one country maybe this is the smoking rate, the lung cancer rate, it may be average is somewhere here. In another country it may be somewhere here. In another country it may be somewhere here. So if you look at this, it looks like there is a very strong relationship. But if you look at the individuals for somehow, within this country, maybe if you look at the individuals, they may be somewhere like this. Right? Maybe even like this. Right? And it can be something like this, or it can be like this. Right? So who knows? Right? So that is what you should look at if you want to really say something about the correlation between smoking and lung cancer. So otherwise, usually this R value will be larger than the actual value, right? Because when you group them, there may be a strong relation, looking a strong relationship. But if you look at the individual, there is a scatter within that, so that diffuses the R value, right? Reduces the R value. Okay, the similar thing here, for example, again. The higher correlation from what is this example? Okay, we have population survey data from US, mean age 24 to 64, correlation between individual income and education, right? So, so then they have got R equal to 0.42. But if instead if you compute the average income and average education for each of 50 states, then your R will be large. But the reason is, for example, if you look at the individuals, education level, for example, education level, if you give a number, right, maybe person yeah, maybe we are looking at several states here. So suppose you have 3 states A, B, C. So their individuals going to be like this: A here, A here, A here, A here, like that. And some B's are here, some B's. But if you consider the average of A's, average of A's is going to be here, average of B's is going to be here, average of all these C's is going to be here. So here it looks like there is some kind of a strong relationship, but in this one it's weaker. Right? So interpreting this one will be giving a wrong idea about the actual relationship, because you kind of forget about the actual variation in the data. Right? When you take in the average, actually the variation becomes smaller. So therefore, this is going to give you a larger R value. So therefore, you have to be careful. Of course, people do these things, but when you are interpreting these things, you have to be careful. That's what you have to remember. Okay, I think at the end also. So morning. Okay, I actually have discussed these things earlier also. When you talk about association, always, especially from observational studies, right? When you want to talk about the association, it doesn't, even though there is a strong association, generally it doesn't mean a causation, right? You can say there is a very high association between X and Y, linear association or something, but generally we cannot talk about a causation unless we do a experimental study, because there are so many other things which may also influence the relationship. Therefore, we cannot say just one variable is causing the other one. Maybe there are so many other things causing that thing also. Therefore, they have to be careful. So I have given you some examples, and I have already discussed these examples. Please go through those. So that's the end. We will we shall do a quick recap in the next lecture also. So I saw you have submitted the assignments, right?
Yeah. Did it last night.
Huh?
Did it last night.
Yeah, both. Yeah, but the other one, for the other second one, you have time.
Yeah.
Yeah.
Shall I stop the video?
Yeah.